This is Lesson 29 in our Calculus 1 series, Integration by Substitution. So far, we have the following basic integration rules. We have that the integral of a constant k is equal to kx plus c. The integral of x to the nth power is equal to x to the n plus 1 over n plus 1 plus c for n not equal to -1. We cover that case in Calc 2. We have that the integral of sine x is equal to negative cosine x plus c. The integral of cosine x is equal to sine x plus c. The integral of secant squared x is equal to tan x plus c. And the integral of secant x tan x is equal to secant x plus c. We also have these two integrals, the one for cosecant squared x and cosecant x cotan x, but these don't come up as much. But what if our integrand, the function inside the integral, doesn't fit one of the rules above? We need more integration rules. And so if our integral is not a basic integral, then we're going to look for a composition of functions, and we're going to use u-substitution. This undoes the chain rule for differentiation. So for example, here we have the integral of x times 4 plus x squared quantity to the 10th power. This is not a basic integral. We certainly don't want to multiply this out 10 times and then multiply in the x. That's not reasonable. So we recognize this as a composition, and we want to use u-substitution. So what does that mean? We want to let u equal the inside function. So here we see 4 plus x squared plugged inside the function that takes to the 10th power. So u is going to be that inside function 4 plus x squared. That's step 1. Step 2 is to compute the differential du, and that's going to be u prime of x dx. So we look at u is equal to 4 plus x squared. Its derivative here is 2x, and so du is going to be 2x dx. Now we want to rewrite our integral in terms of u and du. So we want to take the original integral that we have here, which was x times 4 plus x squared quantity to the 10th, and we want to rewrite it in terms of u and du. So what do we have here? We have a u here inside the 10th power, and now we need to recognize a 2x dx here so that we can put in du. Here we just have x dx, so we need an extra factor of 2 in here. So I'm going to multiply a 2 inside my integral, but to compensate for that, I'm going to multiply a 1/2 on the outside. So now I'm multiplying by 1. This doesn't change the integral, it only changes how it's written. So I'm going to collect my 2x dx, and that together becomes du, so that this integral looks like 1/2 the integral u to the 10th du. Right, we have u in here, this is u to the 10th, and then the 2x dx is du. That's here. And we have the 1/2 on the outside. Now we want to integrate. So this is 1/2 u to the 11th over 11 plus a constant. Now we want to rewrite in terms of x and simplify. So remember that u is equal to 4 plus x squared, and then simplifying we have a 22 in our denominator. Or we could write that as 1 over 22, 4 plus x squared to the 11th plus a c. And this is our solution. Now remember, with integration, you can always check by taking the derivative, so let's do that. Taking the derivative here, the 11 comes down. We're going to have 11 over 22 multiplied by 4 plus x squared to the 10th power multiplied by the derivative of what's inside using the chain rule, that's 2x. And then the derivative of a constant is 0. And so simplifying here, the 11 over 22 is 1/2. Multiply that by 2, that's a 1. So we get x multiplied by 4 plus x squared to the 10th, and that's the function we started with. So when we recognize the composition of functions inside our integral, the process is always the same. It always looks like this. So let's take a look at another example. Here we have sine of radical x over radical x. It's not a basic integral, but we notice that we do have a composition of functions. We have radical x plugged inside the sine function. So we're going to start by letting u equal radical x, or x to the 1/2. And then step 2 says compute du. So u prime here, the derivative of u, is going to be 1/2 x to the -1/2. That's 1 over 2 radical x. And so du is going to be 1 over 2 radical x dx. And so now we want to rewrite our integral in terms of u and du. And so I look at my original integral and I look at what I have here for du, and I think I want to just rewrite this in a different way. I'm going to rewrite it as sine of radical x multiplied by 1 over radical x dx. It's the same thing, I'm just rewriting it so that it's more convenient for what we have here. But notice we're still missing a factor of 2 in the denominator there. We can't call this part du yet until we put a 2 in that denominator. So I'm going to multiply in a 2 in the denominator, but then I also have to multiply it in the numerator as well, so I'll have a 2 outside the integral. And now this 1 over 2 radical x dx, that's our du. This here is our u, and so our integral looks like 2 integral sine of u du. And now it's a basic integral in the variable u. So now we integrate, and that's 2 times a negative cosine u plus a c. And now we want to simplify and replace back with x. So u is equal to radical x, so that goes there, and then we can pull this negative outside. And so we're here, and this is our integral. Let's take a look at another. Here we have cosine to the 4th theta, sine theta, d theta. And just as with derivatives, when we're integrating with powers of sine and cosine, I like to get rid of the shorthand notation first. So instead of this cosine to the 4th theta, I want to write this as cosine theta to the 4th power, so that it's more clear where the composition is. When I write it this way, I can clearly see that we have cosine theta inside the function that takes to the 4th power. And since we have a composition of functions, we're going to let u be the inside function. So we're going to let u be cosine theta here. And then we compute du. So we're going to take the derivative here, which is negative sine theta, and multiply that by d theta. And now we want to rewrite our integral in terms of u and du. But what does it look like we need here? To be able to put in du, we need a negative sine theta d theta. So we need to have a negative sign inside the integral so that it will go with sine theta d theta for du. But then to compensate for that, we also have to multiply by a negative 1 on the outside. Now we can rewrite the integral, and that's going to be negative u to the 4th du. And so we're here. And so now we want to integrate. We have negative u to the 5th over 5 plus a constant. And then we just want to simplify and write in terms of the original variable. So this is cosine theta to the 5th over 5, or the shorthand notation cosine to the 5th theta over 5, with a negative out front and then plus c. And of course, in each one of these indefinite integrals, you can always check your work by taking the derivative. Let's take a look at another. I'll give you a chance to work on this on your own. Here we have the integral of u multiplied by radical 1 minus u squared du. So I want you to use the methods of u-substitution, but notice the variable that we're given is called u. So we can't use a u-substitution. We should instead pick a different variable. Usually the one we choose after u would be w. So here, I want you to make a w substitution. Please pause the video and work on that. We notice that we have a composition of functions here, with 1 minus u squared being the inside function. So we let w equal 1 minus u squared. And then from this we compute dw, and that's going to be negative 2u du. Now we want to rewrite our integral in terms of w and dw. Here we have a u du. We need a negative 2 in there as well. So we multiply in a negative 2 and then a negative 1/2 on the outside to compensate. And now we have a negative 2u du, and that gets replaced by dw. And here we have a radical w with a negative 1/2 on the outside. And so we're here. Now we can integrate, but first we'll rewrite that as w to the 1/2 inside the integral. Then integrating, we have w to the 3/2 over 3/2, and we still have our factor of negative 1/2 and then the plus c. Simplifying here, the 2's cancel, we have negative 1/3, and then replacing w with 1 minus u squared, we're here. Negative 1/3, 1 minus u squared to the 3/2 power plus c. Now let's take a look at definite integrals with u-substitution. Here we have the integral from 0 to radical pi of 3x sine of x squared. So again, we recognize that we have a composition of functions, so we let u be the inside function. And then we compute du. Du is going to be then 2x dx here. Now notice we don't have 2x dx, we have 3x dx. So the first thing I'm going to do is pull this 3 out just to get it out of my way. Then I have to multiply in a 2 in the inside, and then a 1/2 on the outside. And so we're here. Now we want to rewrite the integral in terms of u. So this 2x dx becomes du. Here we have a u, so we have sine u du. On the outside we have 3/2, but we have to be really careful here with the bounds. When you have an integral in x, these bounds are bounds on x. When you rewrite your integral in terms of u, the bounds you put on the integral need to be bounds on u. So we have to change these bounds so that they are appropriate bounds on u. So now when x is equal to 0, what does u equal? Well, u is equal to x squared. So when x is equal to 0, u is equal to 0 squared. It's also 0. So we have a bottom bound of 0 here. When x is equal to radical pi, u is equal to x squared, so u is equal to radical pi quantity squared, and so that's pi. And so the upper bound here is pi. Now we're going to solve this definite integral and never go back to x. We don't need to. We'll take our antiderivative, that's negative cosine u, bounds going from 0 to pi here. So we plug in pi for u, and plug in 0 for u, and subtract. Cosine of pi is -1, cosine of 0 is 1, so we're here. It's really important to use parentheses around your evaluations so that you don't lose any negative signs here, so be careful with that. And so here we have in the inside, we have a 2, and so we have 2 times 3/2, that's 3. And this is the value of our definite integral. So when you're using u-substitution with a definite integral, you don't go back to the original variable. I know what some of you might be thinking. You might be thinking, well, can't I go back to the original variable and then plug in the original bounds? Yes, you'll get the same answer, but this is a smarter way to do it, and this is how I'll expect you to do it on your exams. The idea of changing variables is very important, and I want to see that you know how to do that. Let's take a look at another. Here we have the integral from 1 to 3 of cosine of pi t over 2 dt. I want you to please pause the video and work on that. We notice that our inside function is pi t over 2, and so that's pi over 2 times t. And so du is going to just be that constant pi over 2 multiplied by dt. And so now we want to rewrite our integral in terms of u and du. So notice we have a dt here, but we don't have a pi over 2. So we're going to multiply in a pi over 2 and then a 2 over pi on the outside to compensate. And so now the pi over 2 with the dt becomes du, and here we have cosine of u, and so we're here, cosine of u du with a 2 over pi on the outside. And again, we have to change our bounds to be bounds on u. So when t is equal to 1, what does u equal? Well, u is equal to pi t over 2, so it's pi times 1 over 2, pi over 2. And so our lower bound for the integral on u is pi over 2. And when t is equal to 3, we have u is equal to 3 pi over 2. And so the upper bound here is 3 pi over 2. And so now we can solve this definite integral. We take an antiderivative, we have sine of u. We still have a 2 over pi on the outside, and we're plugging in our bounds of 3 pi over 2 and pi over 2. Sine of 3 pi over 2 is -1. Sine of pi over 2 is +1. So we're here. And we get -4 over pi. Now up to this point the substitutions are pretty straightforward, but sometimes the substitution requires a little extra work. It requires solving for x in terms of u. So let's take a look at this problem here. We have the integral of x squared over radical 1 minus x. We identify a composition, and so u is equal to 1 minus x, and that's definitely where we want to start. And when we do that, du is then negative 1 times dx, or just negative dx. So notice that we can handle the dx, because we'll just have to adjust by a negative sign, that's not a problem. And we can handle this denominator, radical u. But what are we going to do with this x squared? How are we going to write the x squared in terms of u? Well, here's a relationship between x and u. Let's solve this for x. X is equal to 1 minus u, and then we can plug that in here for x. So again, we have to adjust by a factor of negative 1, so I'm going to put a negative on the inside and a negative on the outside. This negative with this dx becomes du, and that's here. We have radical 1 minus x, that's radical u, or u to the 1/2. And then here we have x is equal to 1 minus u, so we have 1 minus u squared up on top. Now we have our integral properly written in terms of u. But what do we do with this now? Well, we can work with this. 1 minus u quantity squared we can multiply out, and then we could break this up into 3 separate fractions and simplify each one before we take our antiderivatives. So we're here. Now we can take our antiderivatives, and we're here, distributing our negative sign and simplifying, we're here. And now we just want to answer in terms of x. And remember, u is equal to 1 minus x. So this is our solution. Now there's one more thing to look out for with u-substitution problems. Sometimes we have a double substitution. So let's take a look at this problem. We have the integral of sine radical x over radical x cosine to the 5th radical x. It looks very complicated. It's definitely not a basic integral. So the first thing we want to look out for is a composition of functions. But what's the problem? We have 2 compositions here. We have radical x inside sine and inside cosine. And then we also have cosine radical x inside the function that takes to the 5th power, right? That's this here. So we have 2 compositions here. And so when we see this, we always want to start with the innermost composition. So what's the innermost function here? That's radical x. So u is equal to radical x, or x to the 1/2, and we start from there. So in this case, du is going to be 1 over 2 radical x dx. And just like we saw in a problem above, we had to multiply by this factor of 2 in the denominator. And we multiply a 2 on the outside to compensate. And now our 2x in the denominator with the dx, that all becomes du. Here we have a u, here we have a u, and we have a 2 on the outside. So what do we have? We have 2 sine of u over cosine u to the 5th du. Okay, but this is still a composition. It's still not a basic integral. So what's the composition we see here? We see cosine u inside the function that takes to the 5th power. So let w equal cosine u. Then dw is negative sine u du. We have to adjust by a negative sign here, so we have a negative in the inside and then a negative on the outside. And now we can rewrite this integral in terms of w. Our numerator is just dw, and we have w to the 5th in the denominator, still with a negative 2 on the outside. And so rewriting this so we can integrate, it looks like negative 2 integral of w to the negative 5th dw. So we add 1 power and divide by that number, and we have negative 2 w to the negative 4th over negative 4 plus a constant. Now we're almost done. We just want to simplify and get this problem back into its original variable. So simplifying, the negatives will cancel and we'll have a 2 in the denominator. And the w to the 4th is brought down to the denominator as well. So we have 1 over 2w to the 4th plus a constant. Remember that w is equal to cosine u, so we're here. And then u is equal to radical x, so we're here. And this is our solution. If you want to rewrite it in the shorthand notation, you can certainly do that, and that would look like that. So again, when we're integrating, we want to see if we have a basic integral. If we do, those are simpler integrations. If not, the next thing you want to look for is a composition of functions. Once you identify the innermost function, set that equal to u and proceed with a u-substitution. You'll see in Calc 2, you'll have many more integration tools, but this is the first tool that we're learning here that's really beyond a basic integral, and that's using u-substitution. So this concludes our lesson on integration by substitution, and this also concludes our Calculus 1 series. Thank you for joining me, and good luck on your final exam.